All right, so we talked about F equals ma, Newton's second law, and how to mathematically look at it. Now, what we need to do, though, sometimes is draw pictures of the way that different things work, especially forces. So that's why this part is part 3, drawing forces. Okay? So the first question really is, how do I even draw a force? Okay? So here's the deal. Okay? A force. The way it works is really, if you have an object, okay, let's say it's a box, okay, and somebody's exerting a force on it. Let's say there's a guy over here, okay, he's exerting a force. You don't need to draw the guy, that might help, but you don't need to draw the guy. All you have to do is draw the force. Now, you start the arrow on the box, and then you move to whichever direction he's pushing, okay? So this would be a force. And now the thing is, you have to label that, because if you don't label it, I don't know if it's an arrow showing me velocity. I don't know if it's an arrow showing me an arrow, like a bow and arrow. I don't know. So you have to label it with an F, a capital F, to tell me that it's the force that's acting on it. Okay, but what if I need to draw a really big force? Okay, so let's say somebody comes along to the same box and exerts a much, much bigger force. The only thing you have to do is make the arrow longer. Okay, that's the only thing that you got to do in order to make a bigger force. Smaller forces, obviously, would be smaller arrows. Okay, it's really that simple. No thickness. Don't worry about that. It's just length of the arrow. Okay, so let's talk about, though, what kinds of forces there are. Now, we're going to talk about 6 different kinds of forces: gravity, applied, normal, friction, tension, and air resistance. Okay, now, force of gravity. Let's say, actually, let's set this up. We have a little situation here, okay? Let's say we have the ground. Now, if you're drawing the ground in a force diagram, you draw just a line with a whole bunch of lines underneath. That shows that it's a solid surface, okay? And we're going to say, I don't know, let's say that there is a safe. Let's see if I can draw this well. Okay? Somebody is pushing a safe across the floor. You know, one of those things that you put valuables in. Okay, so you've got this safe, and we're going to start looking at the forces that are acting on it. All right, so what forces do we have acting on it? Well, first of all, the first force that you really have acting on it is gravity. Okay, now gravity we label as F with a subtext G, not just lowercase, it's subtext, so it's a little bit lower. And Fg, or force of gravity, always, always, always points down. Okay? Always points down. So you can draw a little arrow here. Okay? So in the case of this safe, we can draw a force starting from the safe and extending away from the safe. Okay? Pointing down. Now, we have to label it, because otherwise I don't know what this is. Right? So we label with a capital F, and then a lowercase and subtext G. Alright? That's simple enough, right? Now, the thing is, though, is that there are often, there's often another force that's paired with gravity. Okay? And that is a very weird force, a very odd force, a very different force than what we normally think of. Okay? And here's the thing. If gravity was pulling down, and gravity was the only force acting on that object, like this. Brooks, what do you call this?
I have no idea.
This, I have no idea. Okay. If I let go, gravity will be the only thing acting on it, and then it will drop, right? It will accelerate. The force of gravity will make it go faster. Watch. Hey, what a surprise. Now, the reason the safe doesn't move down is because it has another force that's acting in the opposite direction that is balanced with the gravity force. And that's what we call the normal force, okay? And the normal force always opposes, which means goes in the opposite direction of, but it always opposes gravity, okay? Always opposes gravity, which means it is going up, the opposite of gravity, duh. And, this is key, it is equal to gravity. Equal to gravity. So when we go up here to put it in the diagram, what we have is it's going to be pushing up on it at the same amount. So you have the same size arrow. And the way we label this is, well, we got to do a capital F because it's an F, because it's a force, and then we put the N, a capital N for normal force. So if we go back here, we can write FN as the label. Okay? So the thing is that if this safe was heavier, let me show you this. If this safe was heavier, you would have a much bigger force of gravity, okay? But it's not accelerating, it's balanced. So the force that the ground pushes up on the safe with would be the same size as the force of gravity, right? So, for example, this, when it's sitting on a table, okay, it's got a smaller force of gravity and the table pushes up. You can actually see this if you put a lot of weight on a meter stick. Let's say you put a meter stick in between two books and then you put a heavy weight. You'll see the meter stick actually bend, okay? It's because there's a force pushing down on the meter stick. And then the meter stick, because it has tension, pushes back up on the weight. The forces are balanced. Just like when you pull a bowstring back, okay? You pull it back, you're pulling that direction, the bow's pushing that direction. And when you let go, it accelerates in that direction and shoots the bow, or shoots the arrow. Duh. All right. So we've got gravity force and normal force. Now, you will have a normal force whenever it's not moving up or down. Okay? If something's in free fall, there is no normal force. Okay. All right. Let's go back to some of these other forces. All right? Sometimes you might have somebody, okay, actually, let's see, let's draw this guy. You should be drawing this in your notes too, okay? And let's say he's pushing. He's got very long arms. Let's say he's pushing this object, okay? He is applying a force, and he's applying the force in this direction. Let's say it's a big force, okay? That could change size, but we label it as FA, a capital A, okay? It's an applied force. So down here for the label, you write F, and then subtext, uppercase A. And what we say about that really is just any push or pull. Okay? Any push or pull, okay, by an outside entity. Sorry for the handwriting. Okay, any push or pull by an outside entity. It could be a person, it could be some sort of machine or whatever. It's some sort of outside thing that's coming in and applying a force. Maybe it's to the right, maybe it's to the left, maybe it's down. Maybe someone's pushing down on the safe. Maybe someone's lifting the safe. It's just an applied force, okay? So, again, this might change. This whole diagram might be completely different depending on your situation, okay? But the force applied could be in any possible direction. Another force we have going on here would be the friction force. Now, if you think about it, our label would be F, well, it's a friction force, so it's going to be FF. Both uppercase, one is a subtext though. So friction force. Now, here's the thing about friction. If this thing's moving in this direction, friction would be acting in the opposite direction. And usually it's less than the force, but not always. Okay? And so we label that as force of friction, FF. Okay? If he's pushing the safe in, oh wait, got to reverse this. If he's pushing the safe in that direction, okay, friction is going to be acting in the opposite direction of movement, though. That's the key, of movement. So what we say here is that the force of friction always opposes motion. Always opposes motion, okay? So, if an object is going that way, friction is pushing it back that way. If an object's moving forward at you, it's pushing it back away from you, okay? That's the idea of friction. It always slows stuff down. Friction will never speed anything up. It just doesn't happen. So, force of friction is always opposite of motion. Okay? Now, there might be some other things here, and actually, that's it for this picture. But there are other ways that you can apply forces, okay? Remember that Hobbit thing we talked about with the strings holding Frodo up in the cave? Well, that would be an example of a force that was being applied by a rope which would be the force of tension, or Ft, okay? Frodo had weight. The gravity was pulling down on him, right? And because gravity was pulling down on him, he was actually applying a force on that string, on that silk from Shelob, okay? So there's a force applied through a rope. If you're playing tug of war, you are applying forces through a rope, okay, via a rope. That's all it is, okay? In fact, you know what? Let's draw somebody in here, okay? Let's say somebody else is helping him, okay? Let's say it's a shorter fellow, okay? And let's see, there's his legs, there's his arms, and then he's actually got a rope. Let's see. Do I have another color? Yeah, we'll do red. He's got a little rope, okay? And he's pulling on it, okay? But the force, maybe since he's a little guy, okay, the force of tension is pulling it in that direction, okay? So it's kind of adding up the force, okay? And lastly, there is another force that we will wind up talking about, and that's the force of air resistance, which is just F with a subtext, AIR, force of air resistance, okay? And again, this is just like friction. It always opposes motion. It is always opposite of motion. Okay? If you think about it, okay, when you put your hand out the car window, which way does it move? It moves back because you're trying to go through air. Air pushes it back in a sense, okay? It slows you down. Now, here's the other part about air resistance, though, that is not true about friction. The air resistance is velocity dependent, okay? What that means is the amount of air resistance, the amount of force, is dependent on how fast you're going. Just think about when you stick your hand out the car window, like you should never do. But you stick your hand out the car window and you're stopped. There's no forces acting on it, right? And then you start moving 10 miles an hour. Your hand gets pushed back a little bit, and then you get to 30, it's pushed back more, 50, even more. So the faster you go, the more air resistance pushes back on you. Okay? That's really it for the notes here, but I do want to show you a couple examples of force diagrams. That's what we're really drawing here, okay? So let's say there's a ball in free fall. This is a super easy one, okay? So all we got to do is draw a ball. Wow, that was hard. And the only thing that we have going on here in free fall, we got to think of our forces. So if we go back, we can go through this list. What kind of forces are in there? Is there a gravity force? Well, yeah, I mean, we assume it's on Earth, so there's a gravity force. So we're going to draw an arrow starting at the ball, and we're going to label it Fg for force of gravity. Okay? What other ones might be acting? Is there an applied force? No, it's in free fall. Nothing is pushing it except for gravity. Is there a normal force? Is there a force that's opposing gravity? Well, no, it's accelerating. It's actually free falling. It's accelerating. It's not on a surface, so there's no there's no normal force. Is there a friction force? Well, no, it's not on a surface again. There's no friction. Is there a tension force? No, because there's no ropes attached to it. Is there an air resistance force? Well, let's see. This problem tells us to ignore air resistance. So we're not going to draw air resistance at all. So there you go. That is your force diagram. Now that tells us a lot. That tells us that the net force, okay, the F net, okay, is this force, okay, down here. Now you don't actually have to draw that part when you draw this, but the idea is that the overall force is down, which means it's going to be accelerating down. So if you were to draw this, again, all you would do is draw the ball, and the only force acting on it, ooh, that was bad. The only force acting on it is gravity, so you have Fg. Now another one, you've got a block on a table. What I would suggest is draw a little table, boom, boom, okay? And then you can draw the block. There it is. Now, what's acting on that block on the table? Hey Brooks, is gravity acting on a block if it's on a table?
Absolutely.
She's correct. So we can draw a G, or force of gravity, going down. Now, is that block accelerating in the downward direction? Hey Brooks, Is this block on the table moving?
No way.
No, it's not moving, right? So if it's not moving, that means there's no forces, or not no forces, but there are balanced forces acting on it, which means we have an equal and opposite normal force acting up on the block, okay? And that's coming from the table. The table is pushing up as much as the block is being pulled down by gravity. Therefore, it doesn't move, it doesn't accelerate. Everything's good, right? And that's really it for that one. I mean, you could go back and wonder, well, let's see. Is there an applied force? Well, no, we're not pushing on it. Is there friction force? Not really, because it's not moving, so it's not rubbing against any surfaces, so there's no friction. There's no rope, so there's no tension force. And it's not moving, so there's really no air resistance force. So therefore, that is this example. Now, I will do one quick last thing. I know I'm going over my time here, but you can simplify these even more. For this block on a table, some of you can't draw tables or blocks. That is kind of easy. But if you can't draw anything, like I usually can't, you can just take the object to be a dot. That's it. And so for this one, you could just draw FG down here and then FN up here. But that's up to you. I don't know, maybe you like drawing a bit more and that kind of helps you think about it. I don't know. This is usually simple and less work, so that's why physicists do it, because we're lazy and efficient. All right, so that's it for drawing forces. Let me know if you have any questions in class.